Uploading videos to YouTube is free. And what's even better, the limits on how long they can be and how many you can upload are very generous. A YouTube video can be up to 256 GB large or 12 hours long. So the question becomes, how can we abuse this generosity for personal gain? And the answer is obvious. Find a way to turn any file into a video and use YouTube as free cloud storage. The channels BK Binary and ICITry have done something very similar, and I will link their videos in the description. But I wanted to showcase how I approached this problem and how the techniques I used actually work. Let's say, for example, we want to turn the funniest piece of text ever created into a video file and store it on YouTube servers. So the first idea might be to simply change the file extension to MP4 and try to upload it. So let's quickly try that. We can rename the file using the move command and then try to upload it. Sadly, YouTube will recognize that the file isn't actually a real video and refuse to process it. To differentiate between different file types, a computer doesn't just use the file extension. Many file formats have so-called file signatures or magic numbers, which tell a program what kind of file it's dealing with. The magic number is usually just the first few bytes of a file. For example, gzips start with the bytes 1F8B. We can see this when using gzip and compressing a file and then opening it in a hex editor. And as expected, we see that the first two bytes are 1F8B. On Linux, we can use the file command to recognize a file. And when we try a rename bmovie script, it is still recognized as text, even though it has the MP4 extension, so this won't work. Okay, new approach. Maybe if we add the magic number of a video file, YouTube will accept our data. We are going to use the OGG format. OGG is a file format used for audio and video files. Really is just a container format that can wrap many different types of video or audio codecs. OGG files start with the magic number 4F676753, and the files typically use the extension OGV. So let's try that. First we'll copy our file and change the extension, then we open the file in a hex editor and insert a magic number. Afterwards we'll quickly check that everything is saved correctly. And if we try the file command once again, the file is indeed recognized as OGG. However, when we try to upload, YouTube complains and once again refuses to process our data. This is because the data makes sense when interpreted as text, but the same bytes have no real meaning when interpreted as an OGG container. So we need a totally different approach. If you really think about it, a video is just a series of images. So if we can find a way to turn arbitrary data into images, we could then turn those images into a video. A computer represents uncompressed images as a series of pixels, where each pixel uses 1 byte for the 3 color channels, red, green and blue, giving us 24 bits per pixel. So that's easy, right? Just take the data and store the bytes of the data in the red, green and blue pixel values. I've written a quick program to turn any file into an image, where the image's pixels are just the original bytes shoved into the color channels. If we do that with our unfathomably funny test data, it looks like this. Most of the image is black, because our data is only a couple kilobytes large and a single full HD frame could store 1920 by 1080 pixels times 3 bytes per pixel, around 5.9 megabytes. Now, let's try a larger file, like this legally purchased movie here, encoding the first 5.9 megabytes to fill the frame. After we convert it, the image looks just like noise. But some of you have immediately noticed the problem. We are working with uncompressed images here, and if we tried encoding a 1080p 30fps video without compression, it would take up 5.9 megabytes per frame times 30fps times 60 seconds, around 10 gigabytes a minute. But most video files aren't nearly that large. Our legally purchased movie clocks in at about 167 megabytes for 40 minutes, so around 4 megabytes per minute. This is possible thanks to the magic of compression, where instead of saving every pixel of every frame, we only store the parts that are truly relevant. Instead of storing every pixel in the frame, little details that are difficult to see in motion are thrown away to save space. This is called intra-frame coding. And instead of storing every frame individually, a compression algorithm will only save the differences between successive frames, since most frames are only slightly different from previous ones. This is called inter-frame coding. Finally, the entire bit stream is compressed, most often using something called entropy coding. But real video compression is a lot more complicated than this simplistic explanation. Just for illustration, look at this block diagram for the H.264 standard. We will save the technical details for a different time. So first let's see what happens if we just compress our encoded frame from earlier using JPEG, which is a lossy compression algorithm, meaning that detail is removed to save space. We can do this using image magic. But we immediately see something suspicious. We stored 5.9 megabytes of data in that image and now it's only 400 kilobytes. So where did all our data go? Well, let's have a look at the JPEG. As we zoom in, we can tell that almost all the pixels have slightly different colors and got smeared together in these weird patterns. JPEG approximates blocks of pixels using cosine functions, which works well for photos, but destroys all the data we saved in the pixel colors. To give ourselves more headroom, we can try encoding less data per frame, by only using a 192 by 108 pixel image and then upscaling it to 1080p. That would give us 10 by 10 pixels for each color square. While upscaling, we need to be careful to select nearest neighbor as the upscaling algorithm. Otherwise, our data squares will have their colors blended together. So let's see if this is more compression resistant. We'll convert our image to JPEG again and we can see that our crisp, single color pixels have been blurred and smeared together. But let's scale it back down to 192 by 108. And it looks a lot better than before. But the colors are still not an exact match, even though we had 100 pixels per color when we compressed the image. So we need to change how we turn our data into colors. Right now we're encoding 3 bytes or 24 bits per color square, meaning we'd need to distinguish 2 to the 24 or 16.7 million different colors. For example, can you tell the difference between these 2 shades of orange? Which one is more blue? Kudos if you can, they differ by only 1 bit in the blue channel. The right square is a tiny bit bluer than the left one. Video compression tends to throw a lot of barely visible detail to save space, so we'll never be able to tell very similar colors apart when trying to extract our data from the video. Instead, we could try encoding just a few bits in each color channel. We do this by placing them into the most significant bits of the colors. For example, encoding these 4 bits, 1111. Here we put 1 bit into the red and blue channel and 2 into the green channel. 2 into the green channel since the human eye is most sensitive to green. Compression algorithms usually preserve more detail in green shades. But the simple encoding has a problem. Looking at the red channel here. If the color gets darker by just 1 bit, we get a 0 in the most significant digit and decode our data wrong. We can address this problem by putting a 1 into the first bit that is not used to encode any data, marked here in white. In other words, we add an offset of half or least significant data bit. This way the data bits stay unchanged even when the color gets slightly darker. So let's put this theory into practice and try encoding with the new method. I've adjusted the program to only encode 4 bits per color, and this is what the result looks like. We can see that there are way fewer distinct colors. In fact, all the colors appear multiple times. This is because we're generating 2 to the 1 plus 2 plus 1 equals 2 to the 4, 16 different colors instead of 16 million. Of course, we can now store less data per frame. Only 4 bits or half a byte per color square means 192 by 108 color squares times half a byte is approximately 10 kilobytes per frame. So with this new encoding scheme, let's have another try at encoding and decoding a JPEG compressed image. Once again we do the conversion and compression using image magic, and the result looks quite similar to the original. So let's pick one of the color pixels and try to extract the data. For this pixel, the original color before compression was 40A0C0, which encodes these 4 bits. After compression, the color was 44A0B8, and when you look at the bits, we can see that the relevant bits containing data have not changed. So next we need to start generating a series of frames and saving them as a video. The first problem that arises is that we need to encode 10 kilobytes per frame, and most data is not evenly divisible into 10 kilobyte chunks. So the first approach would be to just pad the remaining bytes with zeros. But if our data contains zeros at the end, we won't be able to tell what zeros belong to the original file and what zeros were added as padding. So in the first 8 bytes of the first frame, we encode the size of our data as a 64-bit integer. And while we're at it, we might as well include a 32-byte SHA-256 checksum of the data, so we know if it got corrupted. Actually, to make it easy to find where our data begins, we will just define a magic number of our own and make it the very first bytes that get encoded. So the header is magic number 8 bytes, data length 8 bytes, checksum 32 bytes. YouTube has a nasty tendency to cut off the first or last frame of a video. This doesn't matter for normal videos, but could lose us data, so just to be sure, we'll add 3 completely blank buffer frames at the beginning and the end of the video. We know when the data starts thanks to the magic number, and we know when it ends since we encoded how many bytes the data is long. Using our master plan, I wrote some code to implement this. I actually started out writing the whole thing in C++, but while doing so I rediscovered my deep-rooted hatred for that language. So a quick Rust rewrite later, we have a working tool. To turn the individual frames into a video and back into frames, I used FFmpeg since it can do scaling on the fly and is very well optimized. The actual video encoding takes between 70 and 99% of the time when converting a large file to a video. So maybe for the first time in history, my shitty code is not a bottleneck. This is not FFmpeg's fault. Video encoding is just very computationally expensive. This works surprisingly well, but we encounter a problem as the files we encode get larger. To some degree, decoding errors are unavoidable, and up to a file size of around 1 megabyte we encounter very few. But as the files get larger, the chance of having at least one bit decoded incorrectly approaches 100%. And since even one incorrect bit could make a file completely unusable, we need to address this. So, error correcting codes to the rescue. I actually spent a few days implementing a complicated scheme using Reed-Solomon codes in conjunction with cyclic redundancy checks, but after almost getting it to work, I found out that the implementation I was using did not support a large enough number of blocks to encode anything larger than a few megabytes, so that was a total waste of time. After that, I decided to use a Hamming code, and even though they're not the most modern or ideal solution, they are very easy to implement. A Hamming 3126 code allows us to correct a 1-bit error and detect a 2-bit error in every 26-bit data block. Even though detecting errors that we can't correct using the Hamming codes is made somewhat redundant, since we have a checksum over the entire amount of data. In order to achieve this, they increase the file size by about 25%, which is a worthy trade-off in my opinion. If you want to learn more about how Hamming codes work, I've linked a very good video by 3blue1brown in the description that goes into the technical detail. The header does not have any error correction applied, so we just include 3 copies for redundancy, since it's only 48 bytes large. All of these things are combined into a software tool called vortexkey. So we can turn a file into a video using a single command, and if we do, it looks like this. The final question now is, how many bits can we fit into a color channel, and how small can we make the color squares before YouTube ruins our data? The 1-to-1 bit pattern and 10x10 pixel data square size were chosen kinda arbitrarily. To determine this, I wrote a Python script that runs a series of tests, trying a whole bunch of different settings and seeing if we can get the data back after compression, and also checking if the file has the same checksum afterwards. This is what one of the test results looks like. In the top line are the settings, the bits per color channel, the output video and data frame rate, the output resolution, and the color square size in pixels. Below that is the result. If the program actually finished without an error, how fast it was at encoding and decoding a test file, how much bigger the resulting video file was than the test file, how many errors were detected in the decoded data, where the first number is the number of corrected errors and the second number is the number of errors that could not be corrected, and lastly, if the file checksum actually matched after decoding. And if we sort all the tests by how quickly they ran, we find that these settings were the fastest, and these produce the lowest file size increase. So 1 bit in the red channel, 2 in the green channel, 1 in the blue channel, with a 5x5 pixel color square at a data frame rate of 30 FPS, upscaled to 4K, seems like the top contender. You could lower the data frame rate a little bit if you want to reduce the chance of unrecoverable errors. And there you have it. Converting any file into a video, allowing you to store your data on YouTube's servers. So in conclusion, it is possible but wildly impractical since you can only store around 50 megabytes per gigabyte of uploaded video. The encoding and decoding are slow, with around 1.4 megabytes per second even in the best case. And YouTube's terms of service forbid you from doing it, risking loss of all your data were your channel to be deleted. I will leave links to the code for the vortexkey tool in the description and leave you with some encoded mystery file to relax/study to. Thank you for watching and happy decoding.